Today's lesson is day 1 for section 9.3. As a reminder of what's going on in chapter 9, 9.1 introduced the basic ideas and vocabularies behind performing a significance test. 9.2 focused specifically on significant tests for proportions. Now 9.3, we're going to focus specifically on significance tests for means. Okay, unless you're told otherwise, on an AP free response question, if you are asked something to do with a significance test, it's assumed that you're going to show the 4-step process. Now, as I've said several times prior to today, they don't necessarily have to be labeled state, plan, do, conclude, but all the stuff that's included here needs to be in that pre-response question. So the first thing you want to do is state, what are you going to test? What's your HO? What's your HA? What's your significance level? Sometimes they tell you what level to use. If they don't tell you, you're typically going to choose 0.05. And then whatever variable that you're using in your HO and your HA, you have to make sure you explicitly define it. Okay, next thing is, what are you going to do in order to test those hypotheses? So 1 sample versus 2 sample, a t-test versus a z-test, mean versus proportion, whatever is appropriate to the problem. Now, each one of the procedures that we do that's inference related in the class, there are specific conditions that are associated with them or with it. So make sure whatever those conditions are, they get checked. Okay, the next, the do step. We're going to talk a little bit as we move through this slide, what to show, what not to show, depending on the scenario. But for the most part, you should be giving your sample statistics, you should be calculating your test statistic, and you have to state your p-value. Now, depending on the specifics of the particular test, there might be a little more, a little less with this. And then, conclusion. There's a definite structure to all of our conclusions for significant tests. You can explicitly compare the p-value to the value to your alpha level, and then you are going to reject or fail to reject your HO, and then you're going to have evidence for or not have evidence for the HA. Okay, so when you're doing significance tests for means, you're looking for random. The data needs to come from a random sample from the population of interest, or it could come from randomization in an experiment, randomization of the treatment groups. Sampling without replacement, the 10% check. For the normal large sample, if we know the population distribution is normal, we're good. If we know our sample size is at least 30, we're good. If we don't have that or that, then we have to examine sample data. And the thing we're looking for with the sample data is no extreme skewness, no outliers. Now, fleshing that out a little bit more, if it is a situation where your sample size is less than 30, you do not know population standard deviation, or it's distinctly not normal, then what you need to do is examine the sample data. And the important thing is, it's not enough just to make a graph on that. Not to make take 3. It is not enough to just make a graph of the data on your calculator when assessing normality. You want to sketch the graph on your paper and make an appropriate comment about it to receive credit. You don't have to draw more than one graph. A single appropriate graph will do. All right, turns out that these are the exact same 3 conditions that we had for doing the confidence interval for means in chapter 8. So there's no difference whatsoever at all between these 2 guys. All right, all significance tests have a test statistic that's associated with it. So for the t-test statistic, which is the one we're going to be using for 1 sample t-test from you, it is your sample mean minus the mean from your HO and your HA sample standard deviation divided by the square root of the sample size. If you are doing a right-handed or a right-tailed test, you are looking for the area to the right of that value. If you're doing a left-handed or a left-tailed test, you are looking for the area to the left. If it is a non-directional or a two-tailed test, you're going to find whatever area that you land on and then double it because the curve is symmetrical. And also, forgot to mention, we're looking at a t-distribution with n-1 degrees of freedom for these particular curves. All right, example. The level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. So it's giving us the raw data. Okay, an average dissolved oxygen level below 5 milligrams per liter puts the aquatic life at risk. Do the data provide convincing evidence at the 0.05 significance level that the aquatic life in this stream is at risk? And then as a follow-up question, given your conclusion in Part A, what kind of mistake, type 1 or type 2, could you have made? Explain what this mistake would mean in context. All right, when you're given the instructions of does the data provide convincing evidence or tests or something along those lines, again, unless you're told otherwise, these types of instructions are implying the full 4-step process. All right, next slide. Everything up here is the same. It's just the same setting we've been working with. The way you're going to start any significance test is you're going to state your HO and your HA. We want to test, or we wish to test. Remember, the HO always has an equals associated with it. A HA is always an inequality that doesn't include an equals. So the level or the value of interest here is the 5 milligrams per liter. So the HO is, it's fine, it's as is. The HA, less than. So if it's less than, and we show that, then we have aquatic life at risk. Now, just as a minor side note, some stat courses, some stat books, some stat websites, for the HO, it's not always just a flat-out equals. So in this case, if the oxygen level is above the 5 milligrams per liter, that's okay. It would be acceptable in many statistical scenarios to have this instead of that. Because there's really nothing magical with it exactly 5. It could be 5 or more. More oxygen is good. It's the less oxygen is the critical thing here. Whatever variable you use here, you have to make sure you specifically define. You should state whatever your alpha level is or your significance level. Alpha level and significance level mean the same thing. If you are not given one, default to the 0.05. In this case, we were specifically told to use 0.05. Okay, same setting up here. That didn't change. Now our plan. Assuming we can meet the conditions, we need to do a 1-sample t-test from you. Okay, the important things here. We're going to do 2-sample stuff, so starting relatively soon. We do z-tests and we do t-tests. We do tests for proportion, we do tests for mean. So all these little parts here are an important thing because ultimately all these different things, all these different tests are going to be mixed on the same page at the same time come our final exam, come the AP exam. So you have to be specific in terms of distinguishing all the different types of inference. So it's good to be in the habit of paying attention to all those details. All right, for the random check, the researcher measured DO level at 15 randomly chosen locations. You can't just say things were randomly chosen or random with a check mark. What's specific to this problem that's indicating the random condition gets met? Now, we are sampling without replacement, but in this case here, if you're talking about a stream, you can consider there being an infinite number of possible locations along the stream. It's impossible to, well, not impossible, but it's extremely highly unlikely that you could sample more than 10% of the stream. It kind of almost doesn't make sense here. Now, we don't know anything about population distribution. Our sample size is less than 30. So this is the most difficult case of this type of test, where what we're going to have to do is look at the sample data. So what you need to do is construct some graph for this data right here. Okay, options are, you could do a dot plot, which is pretty easy to do, sketching by hand. You could do a box plot, which is very easy to construct on your calculator. You could do a normality plot, which is a little bit annoying and hard to copy. Ooh, I'm sorry, this was running off the side of the thing here. A normality plot, that you need to use your calculator for, and it's a lot more work, or you could do the histogram. So the author of this question decided to go with the histogram. The key thing here is that we do not want outliers and we do not want extreme skewness. Those are the things that need to be addressed with this check. So the histogram of the sample data looks roughly symmetric. That's the equivalent of saying there are no outliers. I'm sorry, equivalent of saying we don't have extreme skewness, and it shows no outliers. Now, this would kind of be the bare minimum to mention. Sometimes you'll see included, they'll make the extra statement about this does not give us reason to doubt the normality of the population. It's a nice extra thing to throw in there, but it's usually not 100% required by the rubrics. This showing a good, accurate, well-labeled graph with this statement pretty much nail that particular requirement of the rubric. Okay, now for the do step. They didn't give us the summary statistics on this. What we need to know is sample mean, sample standard deviation. They're never going to expect you to calculate that by hand. Now, if they're not given in this problem, you should state, well, where are those numbers coming from? So using technology, sample mean, sample standard deviation. Get that from one variable statistics on your calculator. We need a test statistic. Probably safer to have shown a blank formula with this. That's like the safer way to go. It would be x bar minus the mean from the ho and the ha, sample standard deviation divided by the square root of the sample size. Probably a little bit safer to show that, then show the numbers plugged in with your test statistic. Anything t related, you should be specific in terms of your degrees of freedom, stated somewhere. And then we need to get our p-value, which is going to come from this command right here. So we need to get the area to the left of that test statistic in a t-distribution with 14 degrees of freedom. So that's your TCDF, lower, upper degrees of freedom, and that will give you your p-value. Now, in the future, we're going to learn some other technology stuff, and you may or may not be showing all of this for all of the significance tests we do. Here is the important minimum that has to be shown. If you're going to give just calculated results with no work, and one or more values is wrong, you probably will not get any credit for the do step. Well, these tests are going to get more complicated as we move through the book, and that's a risk you're probably going to be willing to take. Okay, at the very least, this is what you need to be showing. If you didn't already name the test, that should be named before you hit this point, but if you didn't name it, this is like your last chance to do so. You have to show what the test statistic is, you have to state your degrees of freedom, and you have to state your p-value. That's the bare minimal by any AP rubric. Okay, now our conclusion. We need to compare our p-value to our alpha. In this case, our p-value of about 0.18 is greater than our alpha of 0.05. And we have to specifically either state or show in symbols the greater than, less than. If your p-value is greater than this, then you fail to reject the hub. Once you see your p-value is bigger than that, that's automatically your next statement. Okay, now if you fail to reject the HO, it means we do not have evidence to support the HO. So we don't have convincing evidence that the true mean DO level in the stream is less than 5 milligrams per liter. All right, very often there's an associated follow-up question. So in this case, the follow-up question was, given your conclusion in Part A, what kind of mistake, a type 1 or type 2 error, could you have made, and what would this mean in context? Okay, so I'm a fan of starting off by definition of, like, well, what did you do here? We failed to reject the HO. If you fail to reject the HO, that means it's possible you made a type 2 error. A type 2 error is failing to reject when your HO is true. Or you could replace that with HO being false. That would also be acceptable. All right. Now, what's the consequence of that? If we did, then the true mean dissolved oxygen level, mu, in the stream is less than 5 milligrams per liter, but we didn't find convincing evidence with our significance test. So, here, let's recap here. Our HO was that the mu was equal to 5. Our HA was it was less than 5. So, if we fail to reject this, that means we don't have evidence for that. So, if we didn't find evidence for that, here's the result. That would imply aquatic life in the stream is at risk, but we weren't able to detect that fact. All right, one more example, again from beginning to end with the full 4-step process and with a follow-up question. Here are the lifetimes in hours of the 15 deluxe AAA batteries from the company's simple random sample. So actually there was a little bit of a preview thing here that I think that got cut from here. So the idea here is that the company thinks it came up with a new and better battery, so they want to test it. So from the new batteries, they chose this sample of 15. Do these data give convincing evidence that the new batteries last longer on average? Well, does the data give convincing evidence? That's phrasing right there is implied you need to do 4-step process. If you're not doing the full 4-step process with this, you have no chance of getting any credit. Well, getting full credit. Still possibly get partial credit for what you do. So, what do we want to test? We wish to test the HO, that status quo, things as they've been, the mean is 30 hours. We'd like to show that the mean for the new batteries is greater than 30 hours. If the mean for the new batteries is greater than 30 hours, then we've created a better product here. Whatever variable we use here, we have to explicitly define the true mean lifetime of the new deluxe AAA batteries. They didn't specify an alpha level here. The level of significance is not stated. We will use alpha is equal to 0.05 if conditions are met. And then the way that we are going to test this is a 1-sample t-test from you. So, random, simple random sample of deluxe AAA batteries. It actually never said, yes it did, simple random sample. Okay, it did say simple random sample. A random sample doesn't necessarily have to be a simple random sample. Don't use that phrase if it's not true. All right, now we don't know how many batteries they produced, so we're going to have to assume that that 15 is less than 10% of the company's deluxe AAA batteries. We do not know population distribution. Our sample size is less than 30, so we have to examine sample data. So the dot plot of the sample data does not show strong skewness or outliers. Those are the two things we want to take note of. Now, we could have created a box plot, and if we were using our calculator, that's probably the best one to do. We could do a histogram, we could do a normality plot. Any one acceptable graph would be good. Just make sure you show whatever the graph is that you're using and make note with the what you're looking for. Okay, same scenario. Now it's up to the do step. Sample statistics were not given. So if we're going to be using them in a formula, we want to state where they're coming from. So using technology, doing your one variable statistics, sample mean, sample standard deviation. We need a test statistic. That's the blank formula, plug in the numbers, get the value. Anything T related in this class, you always have to state the degrees of freedom. And then we want to get the area to the right of 1.55 on a T curve with 14 degrees of freedom. So lower, upper, degrees of freedom, that gives us our p-value. And then this is the same step warning thing in terms of the bare minimum you have to state in here is the test statistic, and we actually should label that. I don't know if I said that the first time, but label test statistic T equals your degrees of freedom and your p-value. Okay, conclusion. Because our p-value is greater than our alpha, we fail to reject the HO. If we fail to reject the HO, it means we don't have evidence to support the HO. We can't conclude that the company's new AAA batteries last longer than 30 hours on average. All right, another follow-up question that could be posed in a situation where you fail to reject the null hypothesis is to talk about power. As a reminder, power is defined as the probability of correctly rejecting the null hypothesis. So, a common follow-up question in the AP exam when you fail to reject the null hypothesis is, what could you have done or what could you do to increase the power of the test? The two things that they expect you to answer or address, increasing sample size or increasing your alpha level. Both of those were discussed in detail in a previous lesson. There is the third option to increase the effect size, and as we already mentioned, that tends to be out of the control of the statistician, so it's not something that that they expect you to address on the AP in most situations. And that looks like that's it for today.